Thanks for doing those.
Sure. All right. I'm guessing that's probably all the. Y'all got any more questions over old stuff? All right. Time to move to new stuff then, I guess. So last time, maybe I could zoom out a little bit on this thing, huh? Zoom out. Zoom. Okay. So the last time we talked a little bit about this, we checked to see if these were solutions of the systems of equations. So in 6.2, I believe it's 6.2 is where they introduce systems of equations. So we previously did two variable equations, and we had two equations with two variables. We could do either substitution or we could do that elimination to get rid of one variable. And then we have a one variable equation. We can always solve for one variable equations. We get that solution, we go plug it back into the equation to get the other solution. And so they look like ordered pairs when we did two variables. They look like ordered triples when we do three variables. And so we did this, we plugged in these numbers. We saw, hey, the first one doesn't work. The second one works for all three of these things. And so 1, 2, 3 would be a solution of this system of linear equations, not linear, this system of equations. So now, I'm going to sound a little bit like Morpheus, but we want to enter the matrix. So matrix is, what is it? I think I have a book definition here, probably. And so what the book says is a matrix is a rectangular array of elements. Okay, so what does that mean? Numbers go this way as well as that way, right? They're going up and down and left and right. We have rows and columns. And so we do this thing. It's like the soda. It's R by C. Royal Crown. Okay, 2 by 2. So we do rows by columns. So rows is like you're going to the movie theater. Columns is like the Coliseum, right? And so these are both square matrices, you might notice. This is a 2 by 2, 3 by 3. We call these guys square matrices. There's the definition down there. This is 2 by 3. There are 2 rows by 3 columns. Here's 3 rows by 2 columns. So dimensions n by n, rows by columns. And so commonly they'll use the variables m and n to mean their rows and columns. Okay. So we've talked about systems of equations. And so what we're going to end up doing, we're going to end up solving systems of equations using matrices. If I remember my history correctly, I believe Arthur Cayley was the guy that did a lot of work with matrices. But also I've seen some like work by Newton, and he was just like, he was super close to doing this basically. There's like one little step he left out basically. So it's like, we often give one person credit for stuff, and a lot of times, you know, there's that saying, if I saw any further, it was by standing on the backs of the giants that came before me. There's a lot of work that goes towards something, but it's not always just one person. So a little bit about this. I know this is like the generalized form, but if I have something, you can plug in numbers here if you want. This is just the coefficients off of your equations. So we'll do some examples. This is just a sort of form. If I talk about just the coefficients off of here, that's called the coefficient matrix. I'll almost never talk about that. I will talk about the augmented matrix a lot more. And so the augmented matrix looks like we put all our coefficients. This bar equals the equal sign. So the bar represents the equal sign. And this is going to be the other side of your equation. So it could have the bar, or it could not have the bar. It's okay either way. So I know it's probably like going to bug you. We drop an equal sign in there. It'll be okay. We won't break the rules. Okay. So we did that. Now we want to write these things as matrices. And so maybe, well, let's go throw this back up here. And so essentially what we're doing by writing these things as matrices is, you might notice this has a variable, this does not have a variable. And so basically what we're sort of doing is, instead of writing the variable, we don't want to write the same thing over and over again. It's really like kind of monotonous and mundane. And so what we do is we streamline this thing. And we streamline it by not putting the variable and just using space to represent which variable it is. So this first column is going to be our x. This next column is going to represent our y coefficients. This is our z. Same thing over here. We have x, y, z. Those are things on an x. Those are things on a y. These are things on a z. And so now we're using position to represent where this sort of variable is. And then this is just a constant over here, right? This is the thing without any variables. And so we use position to represent what variable that thing has on it. And so if we do that, we first want to make sure it's in x, y, z equals a constant form. So this is already in that form. And so the first thing I'm going to put here is 3 minus 2. So that's my first row. And so my second row looks like minus 7, 2, and 1. And so this is a two-variable equation. So if we have a two-variable equation, you might notice that produces what, a 2 by 3 matrix. Yeah. So each line represents an equation. So we can take an equation, we can put it into a matrix. The next thing we're going to do is take this matrix, put it back to an equation. So here we have x, y, z. So now we're going to have 2, 3. You also want to like make sure if it doesn't have a number on there, you can look at it as a 1. This should be a minus 1. This should be a 0 over here. Okay. And then they're trying to see, you can put a line in here if you want. You don't have to. Same thing here. You could put a line right here if you want, but it's not mandatory. It could be there. It could not. You should know sort of like what that it's an augmented matrix either way, pretty much. That's one of those things that really depends like what book you grab, whether they put the line there or not. Okay, so this is my x, this is my y, this is my z, this is the equals the constant. So here I'm going to put an x. If I don't see an x, what number do you think I'm going to throw in there?
0.
Yep, there are no x's there. There are 3 y's, there's 1 z, and there is a minus 1 constant. There is a minus 1x, there's a 2y. So if you don't see a number, you don't see a coefficient, it's 1. If you don't see a variable, then it's going to be 0. And the rest we sort of fill in. Questions about this? So, like, I think the key is just to making sure these are in the right sort of like order. After these are in the right order, like this thing, it almost fills out itself. There might be a little bit of things, like if there's not a variable, it's a 0, right? Okay. So write the linear system represented by the augmented matrix. So x, y, z is what we're doing. So these are x's, these are y's, these are z's. What this first one looks like? It looks like a 1x minus a 2y plus a 4z. And then this line is your equal sign, 7. So that's my first equation. If you don't write the 1, that's fine. That's fine with me, apparently not my dogs. Shh. Chill. Okay. So this next one, this is a 2x, 0y's, 5z's, 2x. I guess I'll write it plus 0y plus 5z equals minus 2. So I wrote it, but really, we don't need that 0y anymore. So I could probably clean up this equation just a little bit. I'd probably clean it up and give you that one. And then the last thing is, I write it over here, I guess 3x minus 6y plus 8z is going to be equal to minus 1, coming from that bottom line. So we take the variable off, we stick it in the matrix, we put the variable back on when we take it out. You put your variable on, you put your variable out. Okay. Now we're looking at this thing, x, y, z. So this first line is giving me x plus 3y plus 6z. It doesn't have a line, but that's okay. I know I'm just have x, y, z. So this has to be the equal sign, and that has to be 1. Next thing, I don't have any x's. I have a y. Minus 2z, and this is equal to 3. And then I have z is equal to minus 9. Okay. And so what you might notice is if I wanted to solve for x, y, and z, this thing's already solved for z. And so you might notice this is like a really nice form to sort of have it in. I have this solved for z. If you look at this equation, I can go plug my z in here. So I'm not solving this. I'm being a bit lazy because I'm not solving it. But I could go plug this back in here. I could solve for my y. After this step, I would have my y solved for. Have my y and my z. I could go plug it back in here. I could solve for my x. So things in this sort of form, what you might notice is there's 1s in this diagonal here. There's 0s below it. And so if you've ever been in the military, you might know the term echelon. It means a diagonal formation. And so they call this row echelon form. And basically what it means is down this diagonal here, we have nothing but 1s. We have 0s below it. And we like this form because it's easy to solve for it. Solve for your variables. And so I got question marks. So we really don't care what numbers these are. So this is row echelon form. We're going to talk about something in a minute called reduced row echelon form, which is really similar to this, but we make it even simpler. That's example 3. So then we have this example. Solve the system of linear equations represented by the augmented matrix. And so now we need to write out our equations again. So this is x plus y plus z equals 16, that top line gives me. The second line gives me y minus 4 equal to 30. And this line tells me z is a minus 5. And so if I have z, I can go plug it back into here. Y minus 4 is equal to 30. So y minus 4 times a minus 5 is equal to 30. Y plus 20 is 30. I believe y is 10. So I have my z, I have my y. The other thing I need is my x. So I'll have x plus 2 times y plus z. Equal to 16. X, what is this? Plus 20 minus 5x plus 15 equal to 16. I believe x is 1 then. Let me double check. Did that pretty quick. Okay. And so if I want to put this together as a solution, I have all my pieces. I can put it together as an ordered triple. Okay, so this row echelon form makes things like fairly easy to solve. And so I guess I have a little bit of background in here. Gaussian elimination comes from Carl Friedrich Gauss, the father of set theory. And so if you want to know about things in the intersection of like philosophy, logic, and math, that's probably one of the guys to look at. So he came up with this method of transforming a matrix to row echelon form. So basically he came up with this sort of algorithm. I'm going to kind of go over the algorithm. I don't want to go too much into the details, but there are three sort of things we can do. And so I want you to think about when we're doing elimination. And so for elimination, one of the things we could do is we could multiply the left side and the right side by the same number. So one of the things we can do, multiply both sides by the same number. When we talk about a matrix, what we're doing is we're multiplying an entire row. So multiply an entire row by a number. We can do that. There are three things I think we're going to do. We can swap the order of the equations. So we can swap rows. And then the other thing we can do is we can add the two equations together, and so we can add two rows. And so these are the sort of tools we have. We can multiply an entire row by a number, we can swap the rows, the order of the rows, or we can add two rows together to get a new one. And so this is coming from what we were doing with elimination. All we did was we threw our equations in a matrix, and we're doing these same operations that we did when we did elimination of two equations. Okay, so what do I have? So I'm going to go a little quick over it. Because I will allow you to use technology on this. And so what the first thing that we did here, or the first thing I did in my notes, is I did 2 times my row 1. Something like 2 4 over minus 2. And so I multiplied my first row by 2, and I added it to my second row, and it's going to take place of my row 2. And so if we add these two rows, where's my camera? Here we go. I'm going to get 0, I'm going to get 3, I'm going to get minus 1, I'm going to get 7. Okay. And so next page, right here. What I did between these two, and so I will give you a little gist of the strategy. The strategy is to get your 1 here and then to get the zeros below it. And then you get your 1 here and then you get your zeros below it. And so what I did is I swapped row 2 and row 3. And so we swap row 2 and row 3, but now we have our 1 and our diagonal here. And then this step, I believe I did -3 by row 2, plus R3, row 3. And so I'm doing -3 times my row 2. 0 minus 3 minus 3 minus 7. And I'm doing adding row 3, which is 0, 3. -1, 7. And so that's giving me 0, 0, what, -4, -20. Okay. And so then I think the next step is we're just dividing this last row by 4, or by a -4. And so we do that, that gives us 1 and 5. And so if we do that, now our thing is solved. We can go back, we can write our equations. That bottom thing gives me z equals 5. This next line is giving me y plus z, or y plus 5 is going to give me 9. We can solve for y, we can solve for x. And so you can get the solution 3, 4, 5. And so there is a way to do this. You might notice if we look and go back, look at these steps, they all sort of correlate to things that we did when we did elimination, right? I did -3 times my row 2. Why did I do that? So that when I do -3 times 1 and I add it to a +3, this is going to end up giving me 0 here, right? And so I'm making them the same number but opposites. So when I add them, my variable gets eliminated. And so it's the same thing we were doing at the elimination. Now we've just kind of streamlined the process by throwing these things into a matrix. Okay, this is okay. This will get you there. But what happens if we do nothing but 1s and 0s? And so this is something called Gauss-Jordan. I guess Wilhelm Jordan contributed a little bit to what Gauss was doing. And so now they call this thing Gauss-Jordan elimination. And so this is the process of converting a matrix to RREF. This is row reduced echelon form, or the abbreviation for it. Okay, if we do operations, so I have the operations that we did. We can do some more adding and subtracting with these rows. We can make this into 0. We can make these things into 0. And so if we do this with nothing but 1s and 0s, you might notice this number 3, 4, 5. Maybe that looks familiar to something we were doing with this. That's exactly the solution. And hopefully that makes a little sense, because this first line tells me x equals 3, y equals 4, z equals 5. That's exactly what that thing says, right? And so my solution is 3, 4, 5. So, from what I know about programming, they always say if you're doing the same thing over and over again, don't do that by hand, write a program for it, you know? And so that's sort of what's happening here. This is just a really mechanical sort of algorithm happening here, right? And so what we've done is we've written a program for it. And so now we're using good stuff. Use a graphing calculator to solve. And so you might have noticed I put a link. You might have a calculator, you may not. But I put a link on the first page of these notes. And so if you hit like shift and I believe it's shift or control or something. Is it control or alt? One of those buttons, you can actually follow the link, right? Is it an alt click, I believe? I think y'all are probably lost as me. Okay. So we want to do this with the calculator. I don't want to have to do Gauss-Jordan by hand. That's very monotonous. I've made students do that before. I guess good thing so you don't have to do it. So if I want to put a matrix in my calculator, you might notice this thing says matrix in blue, so I have to hit second. I have to hit the matrix button. If I want to call up my matrix, this is how I call them up. This is not how I enter them. So if I enter my matrix, I have to go over here to edit. And so if I want to put this in the matrix that I call A, well, we got to know this is what? A row by column. This is a 3 by 4 matrix. So I've used that website. It's very similar. You have to put in your dimensions. You have to put in your matrix. So now I put in 1. I put in 1. I put in -1. I put in -2. -1, -2, 1, and 2. That's 0, 1, 1, 1. Ooh, I did that quick. Sorry. So I go edit. I put in my matrix. I put it in. I put it in. And then I guess the important thing to do is we're done editing this matrix. I don't want to edit it anymore. So I have to go to second quit. Okay. I feel like if y'all really had to, I feel like you could probably figure where this thing is going to be on its own. But this is second matrix. If we want to do some math on a matrix, it's over here. That stuff. Let's see. That's cumulative sum. That's REF. That's RREF. So anyway, you can do reduced echelon form if you really want, but this is a lot easier form. So if we want to do row reduced echelon form, we're doing row reduced echelon form. Now I have to call up my matrix. So I hit second matrix, and I go to my name, matrix A. I close it off, and I hit enter. Let's see, 1, 0, 0, -1, 1, 0, 1, 1. Okay. And if you want to draw your line, you can draw your line. That might help you see it. But this is telling me what? X is a -1. This is telling me Y is 0. This is telling me Z is 1. If I want to write this into a solution in ordered triple, it looks like that. And so I guess usually the first question is you're allowing us to use a calculator. So what work do you want to show? I want to see whatever matrix you put into your calculator. So if they didn't give you this, I would want to see this. I want to see the row reduced echelon form that comes out of your calculator. So I want to see this. This, if you can get right to here from ifs, that's okay. You should be able to do this, but I'm really going to look for this, this, and this for your solutions. But I would get in the habit of writing these things down because it would really help you out when we get to other things. Okay, so example 6, solve this. It's the same thing. So I'm going to do this again. I'm going to go to my matrix. I'm going to go over to edit. This is still a 3x4 matrix. I'm doing 1, 3, I'm doing 4, I'm doing 8, I'm doing -2, I'm doing -1, I'm doing +2, and I'm doing a -1. I'm doing a 1, I'm doing an 8, and I'm doing a 14, and I'm doing a 9. So also, I quit out of that. So another thing you can do, if it depends how your calculator is. Sometimes your calculator will show you it all in one go, sometimes it won't. But if you want to see all your matrix there in one glorious sort of window, you can always recall it, make sure you have things entered into that matrix right. And so it looks like all my numbers are matching up. And so now I want to do some math on this matrix. I want to do the row reduced echelon form. So I believe that's option B there. So I go to option B, I go and I recall my matrix. I put my matrix into matrix A. So if you want to do them in different matrices, you can do them in different matrices and save them under different variables. Okay. So this is the thing I put in. This is the thing it's spitting out. So this looks like 1, 0, -2, 0, 0, 1, 2, 0, 0, 0, 0, 1. And so first thing you might notice about this is you asked your calculator to put this thing in row reduced echelon form, and you're like, oh, I'm going to get ones in the diagonal, zeros elsewhere, right? No, it didn't happen. So you asked your calculator to put this in row reduced echelon form. It didn't. Why is that? So if we look here, let me get rapid. We look here at this last row. That might tell us something. If we look at the left side of the equation, I have no variables. But this says something like that. So what does that mean? So we've had something like this before. What does that mean if I get something like 0 equals 1?
There's no solution?
Exactly. So no matter what I do, no matter what I plug in, this is not going to be true. So we've talked about no solution with what? Single variables. We've talked about no solution with 2 variables. Now we're talking about no solutions with 3 variables. And so then maybe like it's like, well, what type of solutions can we have is probably the next question. This is how we have no solutions. We get something like this on the bottom, right? If we go put this back into an equation, it's going to give us some nonsense like 0 equals 1. And so we can have single solutions. We know that. We can have no solutions. So let's look at sort of like what sort of solutions we can have. And so what we're doing in 3 space is we're no longer doing lines. We're doing planes. And so we got to think about how planes can intersect instead of how lines can intersect. And so one way, and this is a very, very sort of special case if you think about it, is they kind of all have to be kind of orthogonal to each other. They can be 3 different planes that intersect at exactly 1 point. And so that 1 point kind of has to be in the middle of all those planes. And so if they intersect at 1 point, that's going to be sort of one ordered triple, one solution sort of thing, right? It's one solution, but it's 3 numbers. So I don't want to confuse y'all with that thing. Okay. It's 1x, 1y, and 1z that go together. Okay. The other thing is you could have 3 sort of planes. and they could intersect at a line. And so we can have lines in 3 space. And so we'll talk about this. But if we're talking about points on a line, there are infinitely many points on a line. There are infinitely many, but it is not all of them. So this is going back to that sort of thing when we're talking about with 2 variable equations. If it looks like things on a line, you have to give me the equation for a line. So we will do that. It looks like an equation for a line. So we will go over some of these and how to do an equation for a line in 3 space. It is a little bit different, but it is doable. The other thing is you could have the same plane. So you gave me 3 different names for the same plane. Then it would be all points on that plane. And so that will also give you infinitely many solutions. Now we want to look at this. We're talking about where 3 planes intersect. And so you might notice if we have one plane and they're kind of like one on top of the other, these 3 things, they're never going to intersect. They're parallel planes. They're not going to intersect. So these 3 are all, they're basically the 3 different ways you can get no solution, right? We ask about how planes can intersect. Well, they can all be parallel. 2 of them can be parallel. And so these 2 will never touch. And so all 3 of them will never touch. Or we can have this sort of like, I don't know what you call this, like a TP sort of shape. And so these 3 will never intersect, all intersect at one point, right? We can find like this line right here, right? We can look at that line. That's where 2 planes intersect, but that 3rd one's never going to touch it, right? Plane number 2 down here will never touch it. Same thing here. We can look at this. This is where 2 and 3 intersect. Guess what? 1's never going to hit this thing up here. So there are a few different ways we can get no solution.
Hey, just for fun, what happens if the planes themselves are wavy?
I mean, they could be. But as long as they're still wavy in the same sort of way, they're still parallel, right?
Yeah.
Yeah.
Do matrices work for that? One would assume they do.
Yeah, I think you just get waviness from doing higher order polynomials. So instead of doing x's, you do like x squareds.
Yeah,
there's a way to put,
as a plane.
Yeah, there's a way to put that into matrices too. We're kind of just doing like first order 3 variable equations.
Oh, yeah, I don't want to make it any harder. I was just wondering. I mean, it just seems interesting.
Yeah. Yeah. Yep. You definitely go more into curvature if you get into calculus and all that good stuff. Okay.
I've got another. So I was able to actually get the matrix into my calculator, which made me pretty happy. But how do you get it to do the RREF? What?
It's okay. So everything is pretty much like, they do a pretty good job of organizing where they put stuff. So it's kind of all in the same sort of matrix thing. So you go over to edit to put it in. You go over to math and you scroll down. It's like option B on here.
Oh, it's option. My mic. Okay, yeah. Oh, okay, yeah. Option B, and then what do you do?
And then you hit second matrix, and you bring
up.
How
do you choose option B? Oh, you hit enter probably.
Yeah, you hit enter.
Okay. Oh.
And then you hit second matrix again, and you call up the matrix that you put it in.
Oh, and then you hit second matrix again to call it. Oh, then 1, hit enter, and then it's there and here again, and there it is.
Yep.
Okay. Oh,
Yeah.
wait. And then, wait, no, so I've got it. I don't have that second, that bottom row you have. It says A. How did you get that? It's gone then. Now I don't, you just cleared the.
Which one? Oh, no, I just did that again. That's from me.
Oh,
Yeah.
okay.
Yeah.
Okay. Okay, thank you.
All right, sure. Yeah, I mean, now's the time to be like getting out your calculator and figuring this out. And if you got questions, now's the time for questions for this stuff. I do appreciate it.
I'm doing it on the website. The link that you sent, it's giving you a lot of options.
It should just give you rows by columns, and then you plug in your matrix, and then you hit enter, and it should show you like all the steps they do. It should show you like all the Gauss-Jordan elimination steps.
Yeah.
And
Okay.
it's the final matrix on there that you really
Okay.
want to look at.
Cool.
Yeah.
Yeah.
It gives you
Nope.
all the nasty details on that thing.
That's great. I was doing this work on the online homework last night, and yeah, it was pretty labor intensive. So this is really nice, actually.
You're doing them by hand?
Yeah, that's the way if you start the online homework, that's what they
Nice work.
have you do. It's
Yeah, they suggest you do them by hand. I don't know if there's anything that they absolutely like make you do step by hand. Let me know. I didn't see anything like that in there, but I might have missed it. Like I don't want y'all to be doing this stuff by hand. Like you should be able to use like some technology on this stuff. It's just like it's really tedious.
Yeah.
I don't think it's super beneficial. There's better
Yeah.
things you can try to
It's
stuff.
not complicated math or anything. It's just a lot of tedious work.
It's just and it's really easy to mess up. And when you
Yeah.
mess up
You
early,
mess one thing up, oh my God.
Exactly. Yeah. Okay. So we want to talk about these solutions. And so this is like, I've rendered it in my calculator already. I know how to do my row reduced echelon form. This is what my calculator is going to spit back out me. And so this is like interpreting these things. And so we're going to look at this bottom row. So I see something like, if I rewrite this as an equation, that bottom row is giving me something like that. And so if I see 0 equals 0, like I'm hoping right away in your head, if you see a true statement, right away you're thinking this thing has how many solutions? How many solutions?
Infinitely?
Yeah, that's
Infinite?
exactly it. I want you to think infinite the second you see this, right? It almost even looks like an infinite sign. It's like, so there are infinitely many solutions. It's not any and every real number. We have to have things that look like a line. Ooh. Yeah. And so what we want to do is we want to write things in terms of this is my y, this is my z. I don't know what these is. But I know that last one looks like z. So that one's easy enough. Now we got to look at these equations. This says y minus z is equal to a minus 3. Okay, so solve this in terms of z. So y equals, what is this, plus z minus 3. So I have my y. I need to solve my x. My x looks like x plus 2z equals 4. So x is what? Minus 2z plus 4. And so now I want to piece this thing together. I want to do x, y, z. My x looks like minus 2z plus 4. My y looks like z minus 3. And my z looks like z. Okay. So this might look a little crazy. But what this actually is this is how you write a line in 3 space. And so, what's in my brain? We have an X and a Y, and then maybe we have like a Z coming in and out of the board.
So my question is if Z can be any number, oh, it's any number on that line. You have to know the line. I say you just substitute 0 for Z and move on there, but I guess you don't know for sure the line
it could
goes
be.
through 0.
So basically, we can pick any real number for Z, plug it in, and that would be a solution on here, right? Because it's going within a line within like free space. And so if we look at this, I'm hoping you see this. This looks like a linear formula, right? This looks like a linear formula. This looks like a linear formula. And so what this is telling me, X tells me left or right. And so this tells me how far left and right I'm going compared to how far in and out I'm going. This is telling me how far up and down I'm going compared to how far in and out of the paper I'm going. So I'm moving like at a linear way towards the left, I'm guessing is what, yeah. So I'm moving linearly towards the left as I come out, and I'm also moving linearly, am I going up? I'm going left and up as I come out of the paper, right? Is what this is telling me. It was a little weird. I don't expect maybe to get all that interpretation. But like this is telling me it moves in a linear fashion. This is telling me it moves in a linear fashion compared to how far in and out we're going. I think you can also kind of look at these things as perspective. If you hold your Z steady, if I'm looking like at the right side of a 3D line, it's going to look like a line. If I like do a different angle, right, on that sort of thing, if I look at the front versus the side view, the front and side view of a 3D line is also going to give me a line, right? So there's a few ways to look at this. It's probably your first look at it, so it probably looks a bit crazy, right? Okay, so that is what you do if you have infinitely many solutions. So I want to go like in a quick recap. You can have one solution. You can have, we had that no solution. When we get 0 equals 1, that. You can have infinitely many solutions. And so hopefully, if we look at this one, let's throw this on here. So this solution is going to give me X is 7, Y is -9, 3. And so I'm hoping you can look at these sorts of things. We have our row reduced echelon form. This last line isn't giving me anything crazy. That's that one solution. I'm hoping those are the quickest, right? The other thing, this is probably the second quickest. We get something that's nonsense. You can tell me right away it's no solution. So these infinitely many solutions, they're going to require a little bit of work. You're going to have to do a bit of solving. And so with that said, we want to look at that last line. And so for part C versus part D, part C, how many solutions are we going to get?
Infinite again?
Yeah, this is going to be infinite, and this is going to be 9, right? No solution? Okay, so that is going to be infinite solutions. So we got to do a bit of solving. Let me grab this. So I know it's infinite solutions. Now I'm going to write an equation of a line. I know it's going to be X. I know it's going to be Y. And I know my Z is my Z. And so now I want to look at those other equations. Have something that looks like X plus Z -2. And I have another equation that looks like Y plus 3Z equals 5. So I want to solve these things. I want to solve for x, I want to solve for y, I want to solve them in terms of z. So we got to do a little bit of work. So I have to subtract the z, so this is minus z minus 2. I have to subtract the 3z, so this is y equals to minus 3z plus 5. And so if I want the solution of this thing, this is minus z minus 2 is my x. My y is a minus 3z plus 5, and my z is z. So I think probably another piece of my advice is to write out your equations. I don't know why people try to skip this or something weird. You have to be able to go from your equations to the matrix and from the matrix to the equation. You are the chosen one. Enter the matrix. Questions about these guys? There's a little bit of work. Those other ones are really simple, I feel like. Like the computer's giving you the solution. Those ones, they make you do a little bit of work to find them.
So if we have ones like example 7 on the test, then I guess does the fact that infinite, or I mean, if it's no solution, then the answer is no solution.
Huh? So if it's infinite, you have to give me this equation. This is part of the solution.
And do we have to? So yeah, so you just want the ordered triplet, I guess, is the
Yes.
answer. Okay.
Yes, I need to see this.
Okay. Cool. Thanks.
Yeah.
Are they going to be on? I guess I should. Quiz will let me know.
Yeah, there should be a few on the quiz. So the test is what, next Tuesday? So I will also have class that day, so you can come ask me some questions during class too if you want.
Okay.
Yeah, but I mean, I know you will. I know you'll do this, but like, y'all have to do this by hand. You have to do this by yourself. I don't like watching me do this. Isn't necessarily gonna like be enough for you to learn these sorts of things. So like, practice these things. Get some good practice in with these linear equations in 3 space. They're a little bit weird, but I think they're doable if you practice them. I believe in y'all. Y'all can do them. Solve the system of equations. So this is what I want to sort of see if I give you a problem like this on an exam, on anything else. I want to see your matrix. 1, 1, minus 2, 3, minus 1, minus 1, 3, minus 1. 2, 1, and 12. So I want to see your matrix. I want you to enter that matrix into some sort of technology. 1, 1, minus 2, 3, minus 1, minus 1, 3, minus 1, 1, 2, 1, 12. And if I did it correctly, hopefully that should be my solution. So I want to see what you put into your calculator. I also want to see what came out of your calculator. So you should have at least 2 matrices in your calculator. At this point, if you can read the solution from this, that's fine. You can just go straight to the 432 if you want. If you want to tell me x equals 4, y equals 3, z equals 2, fair enough. That also gets it. It should really be in an ordered triple. Okay. Oh man, I think we got enough time maybe for this. Most of this one is set up, I feel like. 1,000 tickets were sold for a total of $15,500. The prices of tickets were $10, $15, and $20. There were 200 more student tickets than adult tickets. Find the number of each type of ticket sold. So the first thing you want to do, if you're doing a word problem, it will help you out. I know you don't like to write extra stuff, but like this really does help you out. Define your variables. X is the number of children tickets. Y is going to be student tickets. And the last one is the adult tickets. And so now I have my variables defined. If I want to add X, Y, and Z, what number should I pick? So if I add up all the children tickets, student tickets, and adult tickets, how many total tickets were there?
Well, there's the money is the 15,500.
Yeah, there's money. What do they say?
Oh, 1,000. My bad.
And so if we add up all those three, it should give us 1,000. And so there's a few. They do mixture problems, what they call mixture problems, and this is kind of similar to that. We have one equation that represents just the raw number of tickets. Now we want something that represents money, and so now I want to attach something to this X. Well, this is children tickets. I want to attach the number 10 to that.
10.
Yeah. So I have 10X, I have 15Y, I have 20Z. Think about this. This is going to calculate the amount of money we're making off of this thing. This is like I'm ordering like what? So many apples at 10 cents an apple or something, right? This is going to give me the total for my purchase. And so if I look at the total purchase of the tickets, that's that number you're looking at a while ago. I'm running like out of room every time I think. Okay. So I got X plus Y plus Z is 1,000. I get 10X plus 15Y plus 20Z is giving me the 15,500. And the last thing they say, there were 200 more student tickets sold than adult tickets. So this is one of those things you have to get in the right order, right? 200 more student tickets. And so I'm hoping you read this. The first thing is there were 200 more student tickets. And so the student tickets should be the larger number. And so there's a few ways to think about it, but if we take adults, which is we want to add 200, which is Y, I guess. That's one way to think about it. We can rearrange things to do what Y minus Z is 200. So if there's more student tickets than adult tickets, this is saying there are 200 more of these than them. And so I think we have, this is like equation 1, equation 2, equation 3 right here. So we have our three equations. We need to put them in a matrix. So I'm putting that first 1, 1, 1, 1,000. That should be my first line. Next thing should look like 10, 15, 20, 15, 500. Okay. And then this last line, I have no x's. I have one y. I have a negative on this z. So don't forget your negative signs. And this should be 200. And so now we have a matrix. Guess what we can do now? We can solve this thing. 1, 1, 1, and I have 1,000. I have 10, 15, 20, and I have 15, 500, and I have 0, 1, -1, and 200. And so a quick word of advice, like your calculator, if you're using the TIs, you have to put the negative sign, not a subtraction sign here. And so they do distinguish between negatives and subtraction signs. So you might notice if we put it into our calculator, I'm not going to write this thing down, but you should really write this matrix down in here. So I'm writing it, pretending like it's there. So this is my x is 200, my y is 500, and my z is 300. And so now we're here. We have our solution. We're pretty much there. If I give you a word problem, you should probably give me some words back. So they were, find the number of each type of ticket sold. So tell me something about what, 200 children tickets? Or 500 student tickets? And this is why we define our variables at the very beginning, right? And 300 adults. Sorry. And I'm being lazy and not writing enough words. There it is. Any questions over this? Okay. Man, I feel like if I did this one with pictures, I swear most of you would be out there trying to solve it on Facebook. And then I like you. It's so funny because I see these like memes all the time, and they're basically just these like systems of equations like this. It's like 2 hamburgers and a hot dog. It's like, and it equals this amount of money. And then we bring this and I bring this up in class, and then like nobody knows what I'm talking about. So I don't know. I think it's kind of funny. It's kind of sad at the same time too. I feel like you're just intimidated by math or something. Maybe, I don't know. So I'm just going to jump kind of to the matrix that you should have off of this thing. So 1 sandwich, 2 sodas, 2 candy bars, $9. 2119. And then the last one was it soda and a candy bar. 1 soda, 1 candy bar. I don't have much time, so I'll just tell y'all this one should be enough.
There isn't enough information there to solve it. Like,
No, there's not. You end up getting a 0001 on the bottom, basically, right? I think it gives you a. I'll write it out real quick. 1, 1, 0. So you end up getting something like that. And so what you should notice is this thing. And so what ended up happening, which is a good question, right? Because it's a real question. It's like, hey, I went and bought this and it cost me that amount. If you're getting no solution for something like this, what that's going to mean is that someone got mischarged, right? Mischarged. There's no way for this to happen if your variables are consistent. You know, they're all the same number.
So if that's fucked up. So I mean, because it seems like there's enough information, but it's because it got rang up wrong.
Yep.
So if it wasn't mischarged, there would be enough information for us to solve it, right?
Probably.
Okay. Is no solution good enough for the problem?
Yeah.
On it. Okay.
Yeah, it was kind of weird because the book gave you no solution on something that was a word problem, but it's a valid thing to do. So I think maybe it's a fairly valid thing to go over. And is the last one also? Oh no. So the last one is an infinite solution. So we've done like 2 of these examples here for this section. So this is an infinite solution, and I'm already out of time, so I'm not trying to go over. But if y'all want, we can come work this one next class.
We'll have until midnight on Tuesday to finish the test.
Yeah, that's what it should be.
Okay.
Well, actually, I usually open it up for 24 hours from class date to the next day. Usually it's like 10. Yeah, usually it's like 9 the next day or something like that.
Okay.
Or 10:30. Okay. I think I might even send it to 10:30 or something like that.
Okay, thanks.
Yeah.
Are you around today during office hours?
Yeah, I'll be around.
Okay, I might hit you up, maybe some questions over the quiz, depending on what we cover in support class today.
Okay.
If anybody else wants to join, but yeah, we'll see.
Yeah, I'll be there. I'll also be in class Tuesday, like finishing up, I guess, this last problem and then working on anything I want from the quiz.
Okay.
Okay.
Okay, cool.
All right.
All right, thanks, man. If we don't see you later, have a good weekend.
All right, study hard. Good luck.
Thanks.
Yeah, thanks.